Good morning, everybody. My name is Bassem Ibrahim from Texas A&M University Embedded Signal Processing Lab. I will talk today about Bio-Impedance Spectroscopy measurement system for wearable devices. This is the outline. I will talk about our motivation behind this paper, our objective, a brief background about Bio-Impedance Spectroscopy, our specific aims and contribution, and system description, and performance evaluation, and experimental results, and finally the conclusion. First of all, bioimpedance, it is the impedance of our body for an external applied current. It has a lot of applications now. For example, it can detect cardiovascular diseases, and there is an important signal called impedance cardiogram. It is ICG, as we can see in this second figure, which is very helpful in diagnosis of cardiovascular diseases. For example, in this figure, the ECG, it captures the electrical signal of the heart, while ICG can capture the mechanical signal of the heart and the time of contractions of the heart. So it is very useful in determining the health of our hearts. Another example for the bioimpedance application is body cell mass decomposition, where I can find the amount of water and fats inside my body. I can detect the dehydration and also find the calories consumption of our bodies. And from the advantages of bioimpedance, it is very low power, it is low cost, small size, it can be easily integrated in IC chips, so it is very suitable for wearable devices. So the problem is that this is how bioimpedance is currently measured. It uses bulky devices with a lot of wires coming out from it to the whole body. So what we would like to do is to move it to wearable devices, where we can use it during our daily activities, which will help us to understand our body better and get more information about our health. Also, the current method depends on single frequency measurement, which is called bioimpedance analysis. What we would like to move more toward bioimpedance spectroscopy, where we can measure multiple frequencies to get more accurate bioimpedance measurements. Finally, instead of only making a single time measurement, we would like to have continuous monitoring of bioimpedance. So a brief background about bioimpedance. If we have this segment of tissue, we can measure bioimpedance by applying external current through these two electrodes using an AC current signal. The current will flow inside the body, and then we can use these two electrodes for sensing voltages, which is proportional to the bioimpedance. We use actually this 4-electrode technique to avoid the high impedance between the electrode and the skin. So basically, the bioimpedance, it measures the fluids inside our body. So our body consists of these cells. We have fluids inside the cell, which is called intracellular fluid, which can be modeled as impedance resistance called RI. And we have also external fluids, which can be modeled as RE. And there is a cell membrane around each cell, which can be modeled as a capacitance. When I apply AC current at very low frequencies, this cell membrane acts as a capacitance, blocks the current to go through inside the cell. And at very high frequency, the current can pass through the cells. So we can get this equivalent circuit for bioimpedance, which is act as the internal resistance in series with the cell membrane, and this is in parallel with our external. At very low frequency, the current is blocked, and I have only RE. At very high frequency, I get equivalent of RI in parallel with RE. So the impedance varies with frequency. So if we can plot the Nyquist plot for the bioimpedance, we will get this shape, which is the Nyquist plot plots the reactive part versus the resistance part across the frequency. At very low frequency, I have a high resistive value, and as frequency increases, the resistive part decreases. I start with RE and end with RE parallel with RI. While the reactive part, as frequency increases, it starts to increase till it reaches maximum at this frequency, and then it falls again. So if I can get this plot for the bioimpedance across frequency, I can extract the equivalent circuit, which is has very useful information for other applications. So this is our objective, is to measure this spectrum for the bioimpedance and to be able to estimate the equivalent circuit. So our objective specifically is to measure bioimpedance across frequency to get the Nyquist plot, and at the same time to have continuous monitoring for this spectrum across time. So at the same time, we are targeting wearable devices. So the bioimpedance range should target a small body segment, which has much small impedance compared to the whole body. And we need to have high accuracy in order to measure the variations of bioimpedance on only small body segments. So we cover the frequency from 4 to 120 kilohertz with 32 steps. Each step we are sweeping the frequency. So each step will take 4.7 milliseconds each. And we will plot this Nyquist plot for each 125 milliseconds. This time is chosen to show the variations of respiration rate or heart rate, anything that it changes at the rate of 1 second, we can detect these changes in continuous time. So our contribution here in this paper is that we are presenting a bioimpedance spectroscopy measurement system for wearable devices. We are presenting experimental measurements for bioimpedance spectroscopy from the upper arm. We are also presenting the circuits and the signal processing that allowed us to do this measurement system. We have made experimental results to measure, to capture physiological signals from the bioimpedance, such as heart rate, respiration rate, and muscle contractions. So our system is basically, as we said, we are measuring the spectroscopy by sweeping the frequency from 4 to 120 kilohertz. This is done by a programmable current source formed from a DAC plus V to I converter. We control this DAC by a microcontroller through SPI to sweep the frequency across the whole range. And then we apply this current across these two electrodes, which are placed on the upper arm. The amplitude of the current is 355 microamps RMS, which is compliant with the safety standards. And then we place the two sensing electrodes beside the current electrode, and then we sense the voltage using an instrumentational amplifier, which is very low noise across the supply, plus minus 5 volts. And then we inject the signal to an EDC at 16-bit EDC at 2 megasample per second. And then this is followed by digital signal processing to get the real and the imaginary part of the bioimpedance. Actually, the bioimpedance is the amplitude of the signal sensed here, so we need an amplitude demodulation. So we need to get the carrier signal from the DAC here, which is simultaneously sampled by the EDC, by the second channel of the EDC, and is then injected to the digital signal processing for synchronous demodulation. For the digital signal processing part, we first do a bandpass filter, a third-order bandpass filter around the carrier frequency to remove any DC noise or 60 Hertz interference and any harmonics. And then we do phase and gain correction to ensure synchronous demodulation. And we do IQ demodulation to get the real and the imaginary part. So we need to multiply by the in-phase carrier and the quadrature. We generated it by using 90-degree phase shift. And then a low-pass filter, second-order low-pass filter at F cutoff of 500 Hertz to get the real and the imaginary part. Actually, this cutoff frequency is a trade-off between how fast I will get my update for the spectrum and the noise that I can filter out. So we had chosen this filter to get an update for each frequency step at 4.7 milliseconds, and at the same time, we get an acceptable noise performance that allows us to see all the important variations in the bioimpedance signal. For the phase and gain correction, it isn't important because I need to get an absolute value for the impedance. So any phase error between the sensed signal and the carrier will cause error in the measured impedance. So we need to make this calibration step first at the beginning by using a reference resistor, which is with a known value. So any phase measured, it will be an error that needs to be corrected, and which is measured by dividing the imaginary divided by the real part and taking 10 minus 1 of this signal. This is the phase error, and calculating the gain by just measuring the amplitude of the measured signal divided by the reference signal, the reference resistor. I need to make this to calculate this error at each frequency, because these errors, it changes with frequency. And in order to ensure accuracy across the whole frequency range, we need to make this calibration at each frequency step. For the correction phase, we do this for any bioimpedance measurement by first we correct the phase by dividing it into two steps. First, there is an integer time delay that I can make in multiple steps of the EDC clock. And the residual time delay is done by an all-pass digital filter with variable phase shift dependent on this residual time delay. And the gain is corrected by simple division in the digital domain. All the digital signal processing, this is done on MATLAB in the digital domain. Then we have made system evaluation for the performance by measuring reference resistors with known values. Covers our range from 1 to 120 ohms. And as we can see in this figure, this is our measured values compared to the reference resistor value. And as we can see, it proves that it matches, and it has high linearity for the whole range. Also, the root mean square error is around 0.07 ohms, which is very enough to get all the variations in the bioimpedance. Then we have evaluated our phase and gain correction and make sure that we are measuring the correct absolute values for the impedance. So we have plotted the Nyquist plot, which is plots the imaginary versus the real part of the impedance across the frequency for known resistors and capacitors. We have chosen two sets with resistance 30 and 82 ohms and capacitance for 100 nanofarad to 30 and 34 nanofarad. And this matches the actual bioimpedance range that we are expecting from small body segments such as upper R. And this figure shows that the dots are the reference values and the line is the actual measurement. And this shows that they are matching together for the whole range of interest. So now I have verified that my system can measure absolute value of bioimpedance correctly across the whole frequency range. This is a comparison for this work with a recent paper in 2015 and also a commercial product for bioimpedance spectroscopy from TI. It compares the frequency current, the impedance range, and the resolution. This paper shows that it has higher resolution than the other work. And it has similar specs for the other parameters, but I believe the most important thing here is that we have showed experimental results for bioimpedance spectroscopy from a small segment of the body, as we will show later. So this is the experimental results that we have done on human subjects. We have placed the electrodes on the upper arm using wet electrodes. The spacing between these electrodes is around 3 or 4 centimeters. And then we have measured the bioimpedance spectroscopy by varying the distance between the sensing electrode between 1 and 2 and 3 centimeters. So this blue curve is for 3 centimeters, and the red for 2, and the black for 1 centimeter. As we can see here, the spectrum the Nyquist plot is very similar to the ideal case, especially at the low frequency part, which is this part. We can also notice that the bioimpedance decreases as the spacing between the electrode decreases, and this is also as expected. The impedance, the real part decreases from around 100 ohm to 50 ohms, and the imaginary part from around 18 ohms to 10 ohms for the least spacing. Then in the next experiment, we have showed that we can also capture the respiration rate in frequency and in time also, and this is our main objective. So we are showing that in this heat map, the bioimpedance, which is this color from blue to red as the impedance increases, and this is the frequency from 10 to 40 kilohertz and across time for 30 seconds. As we can see that this is the real part of the impedance. It decreases with frequency as expected. In addition, there is variations in the amplitude of the bioimpedance, shows the respiration rate, and this respiration rate was verified by placing an accelerometer on the chest, as we can see in this lower figure, and they are matching together. The second thing is that we can also capture heart rate by plotting the real part of the impedance across the time at fixed frequency. We can see that there is heart rate superimposed over the respiration rate. So by using a high-pass filter, we can get the heart rate, and we have verified this heart rate using ECG signal, and the heart rate, the average heart rate over the 30 seconds matches with the ECG signal. Another experiment is that we can also detect muscle contractions. If we place the electrodes across the upper arm in like this figure, we can detect the muscle contractions from the real and the imaginary part of the bioimpedance, as shown in these two figures. So these intervals show that the bioimpedance varies with time according to the muscle contractions in the real part and also in the imaginary part. We can also see that in the imaginary part that the bioimpedance is also, as expected, at low frequency, it is low amplitude and increases with frequency and then decreases again at the highest frequency. So in conclusion, we have presented a bioimpedance spectroscopy measurement system suitable for wearable applications. We have presented the circuits and signal processing to achieve accuracy of 0.07 ohms, cover frequency range from 4 to 120 kilohertz, and updates every 150 milliseconds. We have evaluated our system using reference resistors and capacitors, and we have made experimental results for bioimpedance spectroscopy from upper arm. So thank you. I would like to thank my co-authors and thank you for your attention and any questions?
I have a question. What is it about respiration that causes an impedance change that can be picked up in the sensor?
Well, we believe in this experiment that placing the electrodes on the upper arm can capture the respiration rate due to the movement of the upper arm. So in this case, the subject was sitting at rest, and the respiration rate can cause changes in the bioimpedance on the upper arm due to the movement of the upper arm. Yeah.
Thanks for the talk. On slide 10, you had your instrumentation amplifier with a plus minus 5 volt rail. I'm always interested in how this sort of thing's implemented. Did you use a linear bench supply to power this up, like a dual?
For the current source?
Oh, no, just for the instrumentation amplifier. You've got a plus minus 5 volt rail. How did you power that?
This is a discrete component system. So this is a device from ADI that we have used for an instrumentation amplifier.
And the power supply, how is this from a dual bench supply?
Yeah, bench supply.
Supply?
Yeah.
When you take this and actually implement it with a battery-operated single supply rail and come up with all the issues of power supply rejection, do you anticipate challenges there, or do you expect that to be straightforward?
Okay, we have already started in implementing this on a wearable device. So I believe we have two options. We either can generate the negative 5 volts on the board, and I believe this will be a little bit complicated. The other thing, I believe this can also work with single supply. It is possible to work with single supply.
Thanks.
You're welcome.
I think I'm next, sorry. A very quick question. I mean, an obvious application space for this is in your Fitbit type area where, you've got people jogging. Now, if you're monitoring respiration and other bodily functions while the person's on the move and the person sweats, will this not massively change your bioimpedance measurement?
Yeah, there is a problem for sure during hard activities such as running or jogging. There will be motion artifacts, and a lot of problems affect the bioimpedance. There is a lot of work in literature to solve the problems of motion artifacts, but we believe that you can still get you can solve these motion artifacts problems, and also you can detect that you are at rest and get these useful measurements during when you are at rest, using, for example, IMUs to detect when you are moving or when you are at rest.
But aside from the motion artifacts, I mean, you use the real part of the impedance to do your measurement there for the respiration.
Yes.
That real impedance will change according to the contact resistance with the skin, which will change according to how much you're sweating. So if you're running, you will sweat. If you're in a hot country, you will sweat, and this may change your contact impedance.
Okay, this will change, I believe, the skin, the resistance of the skin to tissue, to electrode impedance. And this is completely eliminated by using this four electrode architecture. We are eliminating this skin impedance. So we are measuring the underlying impedance for the cells itself, not the tissue.
Okay.
Not the interface.
Can I go while they're getting the microphone there? So I had two questions. One was, in your state-of-the-art comparison, you were comparing your system versus the AFE chip, which seems to be part of your system. So could you please explain what the difference is between what you're comparing and this work?
Okay. This is a bioimpedance spectroscopy device, but it is actually targeting the whole body measurement. And this is a common commercial product. There is no commercial product available to measure bioimpedance for small body segment, because the bioimpedance is much smaller than the whole body. The whole body is around 600 ohms, while for small body segments it is 100 or 50 ohms. We actually tried to use this product first to measure the bioimpedance directly, but we couldn't, because it has low accuracy to measure the small body segment bioimpedance. This is the main difference between our work and this data sheet and this product.
It's that the range that you're targeting is significantly different.
Yeah. They are working on a big range. Yeah. While we are only concentrating on the small body segment bioimpedance.
And one other quick question.
Yeah.
Can you explain the difference that you observed during muscle contraction due to the change in distance between the two sensors, or between the two leads?
Actually, there are two experiments. First, this is the bioimpedance spectroscopy for changing the distance between the electrodes. There is no muscle contraction here, just sitting and changing this distance. I can get these three figures, okay? The second experiment is for the muscle contractions. Placing the electrodes like this and doing contraction in the muscle, it will change the impedance, okay, of this part. And so that I can see this change in the amplitude with time.
Can you explain that by a change in the distance?
Sorry?
You could make
this
a model.
This is fixed distance. I didn't change its distance in this experiment.
The muscle itself is changing the distance.
Yeah, due to contraction, yeah. But the electrode itself, they are I didn't change the position of the electrode in this experiment.
Yes, but you could make a small model and just see if the difference that you observe is actually due how much to the distance.
This distance between, you can explain this change in the bioimpedance by changing the distance between the electrodes.
Right.
Yeah.
I mean, it would be an interesting follow-up to your study.
Sorry?
It would be an interesting follow-up.
Yeah, that's right. Yeah. This can be future work. Thank you very much.
Could you please go to slide 16, where your experimental results are? 16. Yes, thank you. Do you have an explanation for this shape on higher frequencies? And then I have a second question. The difference between the two distances, or three distances, is about 40 ohms or so.
Yeah.
Is this, did you investigate this? Is this realistical?
Yeah. Okay. For the first question, the trend of this curve is like the ideal waveform. Okay. Especially at the low frequency, it looks exactly the same. For the high frequency, we can see there is some deviation from the ideal case. But for the ideal case, for sure, it assumes the equivalent circuit for the bioimpedance, and this is better matching for the whole body when you measure for the whole body. But here you are measuring only on a small segment of the arm. It has different structure for I believe the bone, the muscles, any fluids in this area can cause this change. The problem, we don't have a reference to compare with to verify that this is also repeatable with other devices. But what we made is that we have compared our system with reference impedance so that we make sure that this is correct. And this is, I believe this is change will be due to the structure of this area under measurement. And I believe this needs more investigation to exactly understand why this is a little bit different from the ideal shape.
Okay, but that would mean when you use 4 or 6 centimeters, for example,
yeah,
you would then be at 150 ohm or so. Or
yeah, as you
ohms.
increase the distance between the electrodes, the impedance will increase. Yeah.
Okay, thank you.
You're welcome.
Thank you, very nice talk. So my question is, if you fix the electrode separation by varying the frequency, do you expect to see any change in the tissue activated volume of the tissue when you take the measurement?
If I fix the distance and
yeah,
then
the electrode distance is fixed. You have, let's say, 3 different frequencies. Are you measuring from the same tissue volume in each cases?
So in this figure, I am fixing the distance and changing the frequency. This is what I have done here. Is this your question, or?
No, like, yeah, the resistances or impedance measurements you measure are changing, for sure. But does it mean that the activated region or the tissue that you actually measure the impedance of, the volume of it, does it change?
No, the volume here is the same. Because I didn't change the electrode. The impedance, it changes because of as I have discussed before, this equivalent circuit causes this change of the impedance with the frequency, but the volume is constant because the electrode are at a fixed distance.
Okay, so electrode separation is the only thing that controls the volume that you're measuring the impedance of.
Yeah, and that's why we have this. The same figure is repeated again at lower amplitudes for smaller distance.
Okay, thanks.
Hi, thanks for your talk here.
Yes.
Thanks for the talk. I'm coming back to the question about the sweating.
Okay.
It will affect the electrode polarization, actually. And have you thought about any mathematical method to correct that effect?
The effect of sweat?
Of electrode polarization.
Of what, sorry?
Electrode polarization. A double layer that can be created there because of the sweating. We haven't seen any problem with the electrode. The electrode we are using wet electrode. It is a silver chloride metal with gel. It has very good contact with the skin, so that we are eliminating any problems with the electrodes now. We are focusing mainly on the circuit, the signal processing. So we don't have any, using these wet electrodes, I believe we don't have any problems with the electrodes right now. In the future, we may use dry electrodes. It will work, and it is more suitable for wearable devices. It may have a little bit higher resistance with the skin, but I believe it can also work with our system, but it will need some we would have some challenges in terms of motion artifacts and this higher resistance, and I believe it can still work.
Thanks.
You're welcome.